please welcome Vice President for Strategic Initiatives and Executive Director of Stony Brook, Southampton, Wendy Pearson.
All right, look at this. Good evening, and thank you. Thank you for standing up for me. This is such a pleasure to look around and see so many of you who've come out for tonight's State of the Bays, No Time to Waste. Now, many of you know that this is an annual event. This year, we decided that we really wanted to broaden the reach. And this turnout is well beyond anything that we expected. And so thank you so much for coming. I think... The research coming out of the School of Marine and Atmospheric Sciences, and from Dr. Gobler's lab in particular, is not abstract. It is directly connected to the health of our waters, of our communities, and the local economy. Now, you know Dr. Gobler is a SUNY Distinguished Professor and an endowed chair of coastal ecology and conservation, and the director of the New York State Center for Clean Water Technology. He and his team and his students, so many of them are here. You got to see their posters, so exciting to see. They're at the forefront of understanding of what's happening in our coastal waters, and just as importantly, what we can do about it. Tonight's State of the Bays, No Time to Waste, is exactly that, a clear-eyed look of where we are and what comes next. With that, I give you Dr. Gobler.
Thanks, Wendy. Well, good evening, everyone. Nice to see so many people here. Thanks for coming and thanks for your interest. I'm going to get right into it. There we go. And I'm going to start by thanking all the fine young men and women who work in my lab. I call them the boots on the ground and the fins in the water. They're really the ones who make things happen. Hopefully you got to see their posters before the event, and if you didn't, talk to them after the event, and I think it's worth giving them a round of applause right now. And I'm going to start by dedicating my presentation to a great environmentalist, Dick Amper. For those who didn't know, Dick Amper, yeah, let's hear it for Dick. Dick Amper was a champion for the environment, and you can see my tagline. He was a force of nature and a force for nature. I spent the summers of 1989, 1990, 1991 going door to door campaigning for the Pines Barrens Act, which actually was finally signed into law in 1993. And, unfortunately we lost Dick this year. But, I would just say anytime you're driving from up island to out east and you're going through some forest, think about Dick, because the Pines Barrens Act preserved 100,000 acres that we'll have forever, and that's a lasting legacy. And I'm so glad that he did that. He was a great man, and he'll be missed. Moving on, though, I'm going to talk about water, and we all know how important water is for Long Island. It is the essence of life for all of us here in Long Island. The water that falls into our island becomes our drinking water source. That's our only source of drinking water, and therefore the activities of land have an incredible consequence on the quality of that water. And the water we don't extract to drink discharges into our surface waters, and therefore this water is critically and doubly consequential for us. And we know over time, as Long Island has grown, the concentrations of nitrogen in the groundwater below our feet has progressively increased to the point of reaching now about 3.8 milligrams per liter on average. And there's been dozens of studies done in the last decade plus. We know where the nitrogen's coming from. There's more people, there's more fertilizer, and even mostly more wastewater that's going into our surface waters. And if we look at the groundwater on Long Island, and we compare it, and specifically in Suffolk County, and compare it to national averages, as shown here in this graph, you look at that first bar, note that's 200 million people in the United States with drinking water concentrations of less than 1 milligram per liter. So where we are, we kind of stand out. We're at the tail end, and there's a lot of variability. There are areas that are even far above that average. There are areas below it. But this does have consequences, as I mentioned, both for surface waters, but I just want to take a moment before we talk about surface waters. I want to talk about nitrogen in our drinking water. And as some of you may know, or many of you may know, there's a EPA regulation at 10 milligrams per liter to prevent something called blue baby syndrome in drinking water. But the question is 10 milligrams per liter the right number? And as it turns out, there's a study being done right now by the EPA looking at that number more carefully and trying to understand, should it be 10 milligrams per liter? And the reason they're asking that question, and I'll just say they're doing this IRIS study. I'll say a little bit more about it later. It's progressing along. But the reason that's getting done is because in the past decade plus, there's been a growing body of literature and papers being published year after year showing that high levels of nitrate in drinking water at the concentrations below 10 milligrams per liter may be harmful to human health and may have consequences for increased risk of cancer. And in fact, towards that end, the World Health Organization considers nitrate a probable carcinogen. And in the last decade or so, there's been this ongoing suite of papers coming out year after year, and I've highlighted in here the ones in bold, just came out in the last year, making links between high levels of nitrate in drinking water and cancer instances. There's also links with potentially with birth defects as well. And I'll point out this one paper here that pretty much says it all. You can see it's using a CDC data set with over 250,000 people, showing a more than 70% increase in the risk of cancer when you go from undetectable levels of nitrate in drinking water to detectable, right? So that's like undetectable would be a lot less than, say it's 0.1, but just going to detectable, 70% increase and an order of magnitude increase in nitrate gives you another 70% increase in cancer risk. And I was contacted in the last year by some scientists at the University of Iowa, right? And so Iowa is a farming state with very, very high levels of nitrate, and they're really struggling right now with some of the highest cancer rates in the country. And thankfully we're not there, right? They have it worse than we do, but we don't want to get there either. And incidentally, I'll be going with my lab to Iowa later this year, and we'll be talking to some of these people. But we can be glad that the EPA is reconsidering that standard. And I start with this, with the basic notion that if this is the epidemiological data with regards to nitrate in drinking water, I think we can all agree we want the nitrate levels as low as possible to protect human health. But let's move on. I'm not a medical doctor, although I do talk to many of them and epidemiologists at the university about this topic. Let's talk about our surface waters. And last fall, my lab put out this map showing what we call water quality impairments across Long Island. And you can see the different colored dots. These are representing either low oxygen zones or harmful algal blooms. And you can see there's not many places in Long Island spared of these events. They go from Montauk all the way into the city. Although I will note, if you know what areas of Long Island are sewered and connected to sewage treatment plants, you'll note that in those particular areas, the incidences of these events is a lot lower and a lot less. But it really is everywhere, and again, many of these dots are harmful algal blooms. And when we think about harmful algal blooms, there's essentially two types in the water. There's those that make biotoxins, and those that what we call are ecosystem disruptive, and don't make a toxin that's toxic to humans, but can lead to fish kills and other adverse outcomes. Now, what's of interest is actually in the last several years, we've had fewer and fewer of those ecosystem disruptive harmful algal blooms. Brown tides have been on the run. Rust tides are still there, not as prevalent as they had been. But unfortunately, that's been offset by the events, the harmful algal blooms that make toxins. And I'm going to start with the ones in fresh water. They're known as blue-green algal blooms, sometimes cyanobacterial blooms. And again, we worry about them because they make toxins. Microcystis is the most common species that we see across Long Island. It makes the compound known as microcystin. And when this compound was first discovered, before it was called microcystin, its tagline was, by scientists, fast death factor, because it elicited rapid mortality in test mammals. And you can see it can be carcinogenic. It also, these cyanobacteria were cited as the cause of a mass death of elephants across the plains of Africa in 2020, which had been a mystery. But using satellite imagery and some other detection techniques, the link was made. So we know that these toxins can be very, very powerful. And we also know they can be a threat to our pets. The CDC published this study showing there's been hundreds of cases of dogs being poisoned by these cyanobacterial toxins. We had a dog die in Georgia Pond in 2012. And over the years, there's been incidences of dogs getting sick in fresh water bodies associated with these blooms. And more recent evidence is demonstrating that these particular toxins can be aerosolized and then be put in the air. So it's yet another human exposure route. Now, there's a very important point here that's known as dose makes the poison. We don't know what the dose is from this, but we do know that this is yet another pathway for people to be exposed. And so while thankfully we're not drinking our surface waters here in Long Island, this is a potential route for exposure. So it's for all these reasons the state DEC is looking very carefully at cyanobacterial blooms all across the state. And the fact of the matter is, over time, since they began doing this, the number of systems with these events has increased. In fact, with last year setting a record for the most water bodies in New York State experiencing these events. And if we break that data down from last year, we can look at all of the counties in New York State that had these events. So in all, it was 53 of the 62 counties in New York State had these events. So they're very widespread. But if you can't see it, that bar all the way to the left that's sticking out is Suffolk County, with 27 water bodies experiencing these events, more than double, approaching triple of the next closest county. So there could be some reasons for this. We're downstate, we're warmer. These blooms like warmer water. But at the same time, Nassau County, which is Seward, has fewer lakes as well, but had one of these events last year. So clearly, excessive nutrient loading is probably at play here as well. And I just want to point out a particular water body here on the east end that is what I call indicative of the do-nothing pathway, right? There's a lot of, I'm going to talk about the things that are getting done to make conditions better. But when that doesn't happen and things are left to their own, things can start going in the wrong direction. So here's Wainscott Pond, which I had never studied before 2014. And we started studying it year after year in collaboration with the East Hampton Town trustees. And what we've seen is that over time, the duration of the events has gone from a single observation to now these blooms are being almost year-round. And the intensity of the blooms increasing as well. So left to their own, these events usually don't get better and oftentimes get worse. And nitrogen loading can play an important role in these events. You can see the title here. It's talking about the dual role of nitrogen. And it's a dual role because it's fuel for the growth of the organism, but also that toxin I mentioned to you, microcystin. I'm not going to do a chemistry lesson here, but what I did is I put up the molecular structure and showed you that this molecule has 10 nitrogen atoms in it. And so essentially, this organism, when flushed with nitrogen, makes lots of toxins. And conversely, if it's starved of nitrogen, it'll make a lot less. So it plays a direct role in how toxic these events can be. I want to switch to marine waters now and talk about the harmful algal bloom that I see as the biggest threat in our coastal waters, and those are blooms caused by Alexandrium. Alexandrium is a dinoflagellate. You can see the picture of it there on the left. It makes that compound saxitoxin, which is a neurotoxin. It's 1,000 times more potent than cyanide. And it can cause something known as paralytic shellfish poisoning. And in places like Alaska, which has a larger coastline than the rest of the entire United States, there can be events that are not regulated and can get people very sick or even worse. And this organism is widespread in our coastal waters. You can see that here with the color-coded points showing you where we've, in red, the very highest levels. And prior to last year, prior to 2024, we had 8 different locations that had been closed to shellfishing because of an Alexandrian bloom and high levels of toxins. And you can see the locations here. You know, part of the event, as you've already heard, is I'm going to recap some things from last year. So I just do want to recap the events with regards to Alexandrian PSP events last year. So as an example, last spring there was a closure in Shinnecock Bay. The entire western half of the bay was closed, being the largest closure in 15 years and the second highest cell densities we'd ever seen. We also concurrently had a closure in Moriches Bay and a first time ever closure in this part of the Peconic Estuary, the eastern part or southeastern part of North Sea Harbor, and an area called Fish Cove. Never been a closure there before. Now, I've been at this game for a while, tracking these events, and when I saw this, it rung a bell, because I had done this study that was published, if you can see the year, quite some time ago. We got 2000, you can see it underlined, 2003. One of the first publications that I put out as a professor here. And the publication was focused on the fact that right next to Fish Cove is the North Sea landfill. And what we discovered there was that the North Sea landfill had a leachate plume of high nitrogen, specifically ammonium, leaching into Fish Cove. And in doing so, led to very high levels of dinoflagellates. Now, never went back to check what the dinoflagellates were, but apparently they were Alexandrium. So this event in Fish Cove wasn't surprising, and we're tracking the same event this year. But one of the more concerning events, or the most concerning event of last year, happened in an area in Southold known as Jockey Creek. And this is an interesting water body in that prior to 2022, I'd never even heard of Jockey Creek. And I'm not sure that anyone had any data on Jockey Creek, but the Peconic Estuary Partnership suggested, there's a water body that we think you should be looking at. So we started doing that. And every week from March into July, my lab sends out a weekly report to Suffolk County and to the New York State Department of Environmental Conservation reporting on harmful algal blooms. So we're all talking to each other and working together. And so we started last year seeing this bloom taking off, and the DEC looked into it as well and judged that this place should be closed to shellfishing. And you can see that happened in mid-April. That closure expanded to neighboring Goose Creek just 2 weeks later. And we were there monitoring this bloom. For an aerial photograph, you get the sense of exactly where the bloom is happening. This seems to have some sort of very restricted flow and the concentration of these algae. But what was remarkable about this bloom was the cell densities that it reached. Now I'm going to put numbers up there. They won't mean anything to anyone. But just for perspective, I've been monitoring for this organism for 20 years. Last year, this bloom exceeded the all-time record in New York State for 2 consecutive weeks. You can see the measurements there. You can see what the prior record was. It was about 1 million cells per liter in Northport Harbor. So this bloom reached 10 million cells per liter, a number never seen before in New York State, again, by an order of magnitude. And, I work closely with scientists from across the country. And, and speaking to people both in the West Coast, Alaska, other places in the Northeast, it's possible that no one's seen levels this dense. And you could see it under the microscope. You could see it in the water. And obviously this is very concerning. Now, the FDA has a closure limit of 80 micrograms of saxitoxin per 100 grams of shellfish tissue. That event in Northport in 2008 got to just over 1,000 micrograms per 100 grams. Last year, it got to 1,800. This is, I should say, data from the New York State DEC. So you can see many times above the federal closure limit and higher than we'd ever seen before. And this bloom was interesting for other reasons as well, because as it declined, we saw another species of dinoflagellate come to prominence, Dinophysis, which also makes a toxin. And in fact, even though the Alexandrium thankfully waned in June, then Dinophysis came. And that exceeded the FDA limits for toxins as well. So this place had 2 consecutive algal blooms with high levels of toxins and was finally opened again in August. And it looks like it's not the end, because this was 2025. Earlier this month, the system was closed again, and just a few days later, all 3 creeks were closed to shellfishing, and they're currently closed right now, as is the western extent of Shinnecock Bay. So that's a lot of shellfish closures. I want to make a comment, though, about shellfish in New York State. Right? These shellfish closures are happening because of very careful monitoring by the DEC. So I just want to point out a few things here about that monitoring. So there's something called the National Shellfish Sanitation Program. It's from the FDA, promulgated out to the states, and specifically the DEC. And so within this particular program, they're there to make sure that the shellfish being consumed are clean. And so if you didn't know it already, every square foot of water and bottomland in New York State is being tested and designated by the DEC as either good for shellfishing, open, bad for shellfishing, closed, or seasonally open. And this isn't haphazard, it's based on data. And in addition to that, any bivalve that gets consumed, or I should say sold in New York State, is completely traceable. That is to say, every single bivalve that gets consumed, you can find out where it was harvested, when it was harvested, and also by whom it was harvested. So it's a very strict protocol. And if you look at where oyster farms are in particular, what you'll find is that they're set up in the cleanest waters in New York State, right? Usually open waters, not in these closed areas and in creeks, but open waters where we find low levels of Alexandrium, and generally those oysters are quite clean. And we haven't had anyone get sick, thankfully. Thanks to the hard work of the DEC and collaborations, no one's gotten sick. And if you ask me what I had for dinner last Saturday night, it was char-grilled oysters, and they were delicious, in season. Okay, but still, we don't want these blooms getting more intense. We don't want them spreading out to these open waters, and we know what the causes are. 2 studies we published for some of the very first blooms showed right out of the gate high levels of wastewater-derived nitrogen fuel these blooms, make them more intense and more toxic. Some of the earliest blooms that for this organism happened in Northport, and I mentioned that to you before, at 1 million cells per liter. And as it turns out, within Northport, the very back part of the harbor, this pointer's really tough, right there, there's a sewage treatment plant that discharges, right? Probably not the best design, and maybe was contributing to these blooms. But in happy news, it was upgraded in 2013. And in the upgrade, it reduced nitrogen loads by more than 3-fold. And so what I want to show you is a before and after this upgrade event. So before that event, before the upgrading of the plant, what you can see is that this area was having literally the largest shellfish bed closures in all of New York State, almost every year. It was in 2013, the plant was upgraded. The loading rates went from, again, 21 pounds per day down to 6.5, and you can see what happened afterwards, right? So a direct effect, dropping the nitrogen loads, less intense harmful algal blooms. But what about in Jockey Creek? Well, we've been looking at that very carefully because these blooms have been so intense there. So we've been doing the experiments where we add more nitrogen or phosphorus to see what happens. We've also come up with techniques for dropping the levels of nitrogen, essentially to get at the question, how much do you need to drop the nitrogen and phosphorus levels in order to mitigate these blooms? So on the first point, yeah, add more nitrogen and these events get more intense. This is an experiment from 2023, but it works in reverse. Here's an experiment from the absolute peak of the blooms I shouldn't say absolutely, the peak period, that 2-week period of the blooms last year, right? And so what this essentially is showing is that when we cut the nutrient levels, cut those nutrient levels by 50%, didn't do anything at all. But when we got to 75% or 90% and compared that to the background levels of nutrients where they weren't being diluted out, you can see we got about an 80% reduction in cell densities. So it works in forward, more nitrogen, blooms more intense, and it works in reverse. Cut the nitrogen levels, you can get these blooms to be less intense. Another thing to worry about with regards to nitrogen is its effect on oxygen. And we know that intense algal blooms create a lot of organic matter that when it breaks down can consume oxygen and lead to low oxygen conditions. As it turns out, dissolved oxygen is one of the few quantitative metrics for water quality that are regulated in the state. There's no standard for nitrogen. There's no standard for phosphorus. There's no standard for algae. But there is a standard for oxygen. And the DEC would say that they don't want oxygen levels below 4.8 milligrams per liter, ideally, and they definitely never want it below 3 milligrams per liter. But if we look at what our coastal waters looked like last summer, we see that almost everywhere we're monitoring, at some point in the summer, failed the test and went below that 3 milligrams per liter. And the question is, does it matter, right? And it's a fair question to ask. If we've got a standard and we're violating it across the board, well, maybe that's fine, and it's just the way it is. Well, one thing I want to mention with regards to oxygen is its day-night cycling, and this is really important. Oxygen levels can be very high during the day, and it's actually at night when they become a problem because there's no photosynthesis. So essentially, you have oxygen being injected into the system via photosynthesis during the day, and oxygen being removed at night. And just to give an example, I'll go back to Wainscott Pond. This is monitoring we did last year. And on the left, you're looking at the measurements that were made during the day. And you look at those numbers, got a little jumbled there on the transfer of the slides, but put the dashed line at the 4.8, and you can see everything looks perfect. And that's because my student Jack Thrain was there during the day, measuring, looked fine. But Jack also put a water quality sensor in the water to let it run 24/7. And so when you measure all the time, what you see is that almost every night, the oxygen levels are going down and getting low. And it goes through this day-night cycle. In fact, if we went across the street to Old Fort Pond, where we have our marine lab, and we looked at the oxygen levels in the summer, this is very commonly what we'd see. High levels by day, low levels at night. Maybe it's all fine, right? This is just natural, right? It is natural. Photosynthesis, respiration, but the DEC made it the standard at 3, and maybe that they should just worry about it during the day. So I had a student, Jeff Kramer, who might be in the room. Jeff, are you here somewhere? No, maybe another room. It's in the overflow room. Anyway, he did his master's thesis looking at this question, and specifically set up in the marine lab across the street, where he brought the water in from Old Fort Pond, vigorously aerated it, and then put in a series of buckets, different types of bivalves, one per experiment, and he essentially had 2 treatments. He had the raw water coming right in from the ecosystem and the water that was preconditioned, and by preconditioning it, he rose those oxygen levels above the 3 milligrams per liter. So we could directly ask the question, does it matter that at night, just for a few hours, the oxygen levels are getting a little bit low? And what he found out was, yes, it does matter. And that he could double the growth rates of some shellfish just by adding that extra oxygen and having continually high oxygen. And you can see, you could almost predict how much of a growth rate increase they'd have based on how much hypoxia was happening. And the fit for that relationship was great for oysters and scallops, not as great for clams. So we followed up on that this year. But the last thing in that paper was just modeling out, Old Fort Pond wasn't that bad. Right? We just had an hour or so of just below 3. There's some systems that are really bad, where the oxygen goes down to 0. And so when we looked at all these 24 sites and tried to understand how much could the growth rates increase, we got numbers of 200%. It's just a model, but looks like that could be important. So we tested that model last summer. We went to the Forge River Estuary, well known for having low oxygen in summer. And we had 3 sites, 1 that was kind of open and 2 that were closer to the back, and grew clams, because we knew clams are very hardy, the most hardy of the shellfish to low oxygen. And to see, do they care? And the answer was yes, right? Their growth rates were different. And interestingly, the number they were different by was that same number, about 250%. But what was interesting is when we looked at the average oxygen levels, on average, the oxygen levels were almost the same. And even a little bit higher where they were growing slower. So what's happening? Maybe the standard doesn't matter. Well, things began to fall into place when we looked at the chronic oxygen levels. And what we found is that the area that actually had the lower oxygen, this bottom one, also had the least dynamic oxygen and stayed above that threshold, never got down below 1. But you can see the wild swings in these other sites, experiencing, again, what I call nocturnal hypoxia, low oxygen only at night. So we looked at the averages, everything looks perfectly fine. But what about what's happening at night? And you can see what's happening at night. It's getting very low. And in fact, if you add up the number of hours the water is hypoxic, it lined up almost perfectly with the growth rates of the clams. And in fact, I show this here, and this is maybe one of my favorite slides, in that you can see, look, I'm a scientist, I'm a nerd. I'm gonna own it right here. Look at the R squared value, 0.9989. What that means is that the growth rate of the clams was being controlled. You could explain the growth rate of the clams with hypoxia with a 99.98% or 89% certainty. And that was with regards to its growth rate and also their final weights, almost as good, right? So it's not the average oxygen. It's not the oxygen during the day. It's the oxygen at night, and it's those hours of hypoxia. And this has an ecosystem consequence as well. And that ecosystem consequence is the longer it takes a clam to get to what we call the predation refuge size, the lesser a chance it has to actually live in an ecosystem setting, right? Most of the small clams don't make it because predators like crabs are just going to eat them. And if it's taking super long for them to grow, well, they're never going to make it. So this oxygen does matter for shell fisheries. I'm going to pivot a little bit now and talk about climate change. And I'm sure we've all heard the term Anthropocene and the idea that we're in an era now where the activities of man are overwhelming and the main control of what's happening in the environment. And it's important we consider this as we think about our coastal ecosystems. Now, 2025 wasn't the warmest year on record. It only came in at number 3. But you can see it's right in there with the warmest of all the years. And I won't go into the details, but believe me when I say, because it was a La Nina year, the Earth was blowing its air conditioner as hard as it could. And that air conditioner is getting turned off right now. So we'll see what happens with that. And I could talk to you what I meant about that if you're not sure. But and despite the fact it wasn't the warmest year, it was hard to find a corner of the planet that didn't have above average temperatures. Now, we did just have a pretty cold winter, right? So, and in fact, if you looked, it was so cold, we came in at number 45 in all time for measurements of winters going back to the late 1800s. But believe it or not, the March that just happened in the United States was the warmest ever on record. Not necessarily for us, but more importantly, I want to focus on summer and the fact that in summer, our water temperatures are increasing at 3-fold the global average. And that has consequences. Firstly, it can bring a lot more rainfall, right? It gets warmer, there's more evaporation, there's also more rain. It becomes more tropical. And in the Northeast U.S., if you look at changes in these heavy rainfall events, it's been about a 60% increase since the middle of the 20th century in the Northeast. And a recent study looking at just this century rainfall patterns showed that the 100-year storm is now happening less than every 5 years in our neck of the woods, right? We're in a unique area where we're getting more and more precipitation. And this has consequences for nitrogen loading. This science paper published a few years ago essentially said that the increased rainfall alone is going to be increasing nitrogen loads by 1/3. And it's not all across the country, but again, we are in the epicenter here. More rainfall, pushing more groundwater out, and pushing more nitrogen in our coastal systems. So that's something that we need to bear in mind, with nitrogen as a driver of things like harmful algal blooms and hypoxia. But temperature changes alone have consequences as well. Here's a map of planet Earth on the warmest day ever. It's in 2023. And it's a known fact that in the ocean, organisms migrate towards the poles to stay in their thermal optimum. And we therefore have what we can sometimes call the tropicalization of our temperate waters. But you can have microbes that you don't expect showing up in your coastal waters. And so I want to now talk about a microbe, specifically Vibrio vulnificus. And so what this plot here is showing is the temperatures in Florida and Texas and the cases of Vibrio vulnificus infections in those locations. And essentially and note it's hundreds of cases per year. And it's at the highest temperatures that you have the most cases. So what is Vibrio vulnificus? What do we know about it? Well, don't take my word for it. Let's listen to the CDC. This is an organism that's known to really like warm water. It's known to like brackish water. It's known to infect open wounds. It can affect shellfish. People who are immune compromised are the most vulnerable to this bacteria. They're 80-fold more likely to get blood infections, for example. And then in addition, what does this bacteria do? Well, it leads to the death of flesh. And CDC webpage, so I'm just the messenger here, when people are infected, 20% of those people die within 24 to 48 hours. Just a fact. Okay, and it likes warm water, it likes brackish water. So for example, when Florida got hit by a double hurricane a few years ago, they had almost 100 cases, 13 people died. Okay, so this had been strictly a tropical phenomenon in this country. So in the 20th century, Vibrio vulnificus cases occurred only in the Gulf of, I'm not sure what I should say there. We'll go with the Gulf of Mexico. Just a little humor, I'm not trying to be political. So in the 20th century, it was only in places like Florida and Texas. But in this figure here, what you can clearly see is through the 21st century, it's migrated up the coast. And this paper came out in April 2023 and noted that by that time, it had shown up in New Jersey. And the question was, well, when will it reach the Northeast? When will it hit New York? Well, in the same paper, they ran a model. This is what scientists do. They look at different emissions rates for CO2, and then from there they can project at different points in time how temperatures may change, and then project where the organism might end up being. So here's two time frames, middle of and the end of the century, two carbon emission scenarios, and what you can see in the lower right is that the prediction was, in this paper in April of 2023, that under the high emission scenario, by the end of the century, there will be Vibrio vulnificus cases in the Northeast. Well, 5 months later, the paper was proved wrong, because it was just 5 months later that there were actually the first 3 cases of people dying in New York waters or Long Island Sound waters from Vibrio vulnificus. And I crossed out oysters there because it's a misleading headline, because in this particular case, these infections were skin infections. But at the same exact time as this was happening, or right after this happened in August of 2023, the CDC put out an official health advisory to the entire country, to doctors, saying, be on the lookout. This is happening now in places we didn't expect it. So with that, my lab began monitoring for Vibrio vulnificus in coastal waters. We came up with what's known as a digital PCR assay, and we partnered with Suffolk County, collecting that data, reported that data out every summer, July and August for the last 2 years. And so what I'm showing you here is the maximal densities of Vibrio vulnificus in coastal waters. And you can see there's some diversity, some areas with higher levels, some areas with lower levels. But I want to talk about this because it's a very serious human health issue, right? And it's one of high consequence. I can't change the fact that the medical outcome is people who are infected, there's a 20% mortality rate. That's not I can't affect that. But what we can talk about besides that incredible consequence is probabilities. Okay, so in Galveston, Texas, where they have a lot more of these cases because it's a lot warmer, the chances of getting a Vibrio vulnificus infection, you can see the number here, 0.00035%. To our knowledge, in New York State, since 2023, there's still only been those 3 deaths. So if you do some math and some assumptions, that's a 1 in 10 million outcome for people who are going to the beach, right? So high consequence, low probability. You're 50 times more likely to drown than you are to get one of these infections. And this is a controllable risk. One of the most common routes for this is the bacteria getting into an open wound, right? That's a pathway for this organism to get into the human body. So some common sense measures can get that risk down even lower. If you have an open wound, make sure it's covered, and particularly in summer. And if it's really bad, maybe wait for it to heal a little bit. And we also know, again, as people who are immune compromised, who are at greatest risk, 80-fold higher likelihood of a blood infection. Okay, so we know what the consequences are, we know what the risks are, and it's been I will just admit to you all right now, it's been a little bit of a weird week for me. I don't know if anybody uses Instagram, but there's a crazy Instagram reel going around where it starts out with me saying, you have a 20% chance of dying. And it goes down from there. Okay, so but a less than 1 in 10 million risk. So the question is, I've gotten the question, and it's actually, I hate to hear it. Should we go in the water? All right, so let me give some perspective. Showing a picture of my daughter. Now, that's an old picture of my daughter, 20 years ago. She's now, I'm very proud of her, doing a master's degree in public health at the University of Barcelona. But this picture is important because that's her getting swimming lessons at Tiana Beach, offered by Southampton town. And all of my children got swimming lessons through the town. We signed up with the town to get swimming lessons at Tiana Beach, and it was great, right? And guess what? If I am ever so lucky to be a grandfather, I hope those grandkids will go right to Tiana Beach and do the same exact thing, right? And moreover, that's me. I'm an open water swimmer. I can't wait for June for the water to get a little bit warmer. That's me in Shinnecock Bay, right? And when it warms up, unless I've got some catastrophic injury, an open wound, or if there's some incredible flooding in a given day, I'll be out there every time I can. Okay, so I skipped over the point that, our surface waters are not something to fear, but something a great resource for us all to enjoy. That being said, this is a high consequence event, right? And we want to minimize the probabilities. Even if it's 1 in 10 million, it's higher for some people, and we need to protect everyone. Right? And I'm not just looking out for me. We should be looking out for the people who are the most vulnerable, the immunocompromised, the elderly. Right? So what can we do to make these events as unlikely as possible? Why is it here? What's driving it? And what makes it more probable? What makes it less probable? Quick side note on a little bit of microbiology, and an interesting guy, his last name Bas Beckings, Dutch microbiologist. This guy is so interesting. A side story about him, he was in the Dutch army in World War II. He was captured by the Nazis and thrown in jail. He thought he was going to die. And he had already written one of the most influential textbooks in microbiology. And in his time in prison, with a pencil, he wrote his next textbook, 388 pages over a several-month period that he ended up actually being able to publish because he actually got out he got out because World War II ended, because he was captured in 1945. I love Bas Beckings because he left us this incredible, simple, but very true statement when it comes to microbes in the ocean or in any aquatic environment. Everything is everywhere and the environment selects. If you went in the water last year, you probably bumped into Vibrio vulnificus, no matter where you were. right? It's everywhere. But it's the environmental conditions that make this organism flourish, right? If you just bump into the organism, you're not going to get an infection, right? But if it's at very, very high densities, you could. So the question is, what are the environmental conditions that make it more likely, right? Which we obviously want to minimize. Okay, like I said, as soon as this event happened in August of 2023, within a week, my lab was sampling from this organism. So we've been making measurements all across Long Island in 2023, 24, 25. And here's some of that data. I'm showing you the concentrations of the organism with temperature and with salinity, right? And so we can just make some first order estimations of what's driving things here. And it's consistent with what I already told you, the DEC said, but it's true for our waters as well. When it's cold, you don't see a lot of it out there. And it likes that lower salinity. Note here, if I can get this pointer to work, well, you can see it. At that very, very high salinity, I don't know how far I got to go over here. The levels are very, very low, right? And so because they're so low at those high salinities, that's telling us ocean beaches, it's almost not there at all, right? It's those lower salinity areas. And in fact, when I showed you the map, all the areas that were high were lower salinity areas. Okay, so high temperature, low salinity. We've been doing some experiments trying to understand what makes this thing grow faster. And Ruthie Drinkwater, hopefully she's in the room here somewhere. She was in the building earlier. She had a great poster out there. She's working very hard in these experiments. And essentially just taking water with low levels of this organism and then adding some different compounds to see what are the consequences. So here's adding glucose, simple sugar. And in doing so, in 24 hours, a 50-fold increase. We've done experiments with sand-filtered wastewater, thanks to the Center for Clean Water Technology. And you can see in 24 hours, a 170-fold increase. And now here, algal organic matter, essentially taking a dense algal bloom, lysing those cells and feeding it to the Vibrio, more than 200-fold increase in 24 hours. Right? And I'll tell you, I've been doing these sorts of experiments my whole life, going all the way back to graduate school in the 1990s. I've never seen responses like this. So this is like rocket fuel for this organism. And on the front of algal organic matter, just backing it to nitrogen, these are just a handful of many, many experiments we've done for many, many years. In the summer, add more nitrogen, you get more algae. It's just a very, very repeatable outcome. And so this infographic here tells you, what increases that probability of Vibrio vulnificus? Well, it's higher temperatures, right? It's lower salinity from more and more rainfall. It's also the nitrogen that's fueling those algal blooms, right? And all those things combining to make these events more likely. And, we could play the game from Sesame Street. One of these things is not like the others. All right, one of these things we have direct control over, and that's the nitrogen loading. So I want to transition to talking about that. Clearly, there are some problems we need to address in our surface waters. And happy news, we have the solution. Okay, and let's look at some success stories. And I specifically want to now look at Long Island Sound. Largest estuary in New York State, third largest in the United States by volume. Plan was put together by EPA in the 1990s to reduce nitrogen loads by 60%. An audacious number that cost billions of dollars. But you can see in space what happened. Anything that's in the yellow, the orange, the red, that's all low oxygen conditions that are harmful to marine life. With the implementation of the plan and the reduction of 60% of the nitrogen load, you can see what happened. And just to show it graphically now, starting in 2003, in the very, very beginning, there was some but not really dramatic changes, and people were thinking, maybe this was not the right investment. But as time went on, the levels got lower and lower. The dead zone's now 90% smaller than when it was just at the beginning of the century. Right? Pretty quick timetable. And that's in the face of climate change. So again, the R squared here, not as good as the clams, but still pretty good. Essentially saying that you can predict the size of that dead zone with 75% confidence, or 75% of the size of that dead zone is controlled by the nitrogen loads. Okay, and we live in remarkable times when it comes to addressing nitrogen loading, right? On Long Island, there are more than 400,000 on-site septic systems discharging directly into our drinking water source, and thereafter the groundwater discharging into surface waters. But we live in a county that's incredibly progressive when it comes to addressing on-site septic systems. I often say Suffolk County went from worst to first. Suffolk County, just a decade ago, was getting sued by the EPA for the practice of directly discharging wastewater into our drinking water source. Right now, Suffolk County has a more progressive program for addressing these problems than any other county in the United States. Just a fact. And in the sub-watersheds plan, as shown here, what you can see, in the hot pink, the areas that are the highest priority for upgrading septic systems. Wrong pipe. And what you can see in that hot pink line is that this is not just someone said, okay, we'll just do within 5 feet of the coastline, 10 feet of the coast, 5 miles, 10 miles of the coastline. But rather, they said, let's protect our drinking water sources, where there are wellheads that are feeding hundreds of thousands of people public water. And let's protect the water bodies that are most sensitive, which are the ones on the South Shore, frankly. And they've modeled out what happens if they implement this plan versus not doing it. And if you look at the colors here, you can see there's a lot less of that red, orange, and yellow if we implement this plan. And so the plan is for putting in these advanced septic systems that take nitrogen from 100 milligrams per liter down to less than 19. At the university, I direct something called the New York State Center for Clean Water Technology, where we're harnessing science to engineer clean water solutions to protect public health and the environment in New York and beyond. We've created something known as nitrogen-removing biofilters. These are made from very natural products, sand and wood chips. They've been provisionally approved for use in Suffolk County. They perform as well as or better than almost any septic system tested in Suffolk County. And just so you can see, that bar on the right is if you do nothing, 100 milligrams per liter. These systems are getting down to around 10. And beyond removing nitrogen, they're also removing all sorts of personal care products, pharmaceuticals, drugs, things we don't want getting into our drinking water sources, and doing them at rates that are just as good as sewage treatment plants. And, folks, there's no time to waste. Have you heard? There's no time to waste. They're literally giving these systems away for free. There's a combination of grants right now, essentially from the county, the state, and the towns, where if you live outside of East Hampton and Southampton, you can only get $45,000. But if you live in Southampton and East Hampton, you can get $65,000 in grants to upgrade your septic system. No taxes, no consequences. It's not a loan. It's free money. And this would, for most homes, will cover the full construction. And I think Tom Varley is here. Oh, he is here. And Tom Varley is the man on the case. If you're interested, he's got a table. Tom, you got your table there? Raise your hand again. You can see him in the back. You see his picture here. Talk to Tom. It's not the easiest process, but he can get you through the whole process. That step one is getting the grants. Let him help you get the grants. Get the money first, right? And once you're approved, then you can decide you're going to go forward. But, if you know you're getting $65,000, it might be good to take the plunge thereafter. Okay, very last thing I'm going to talk about is the fact of the matter that while we upgrade these septic systems, it's going to take time to get it done. It's going to take time for the groundwater to flush out of our aquifer. And so we need what we call in-the-water solutions as well. And in exciting news, those are emerging also. very, very briefly, I can't help but point out this paper. It's several years old now, but the Shinnecock Bay Restoration Program, you can get this paper. It's free online. Mike Dole and I put in a tremendous amount, and many, many other people put in a tremendous amount of work into this. It's going back to 2012, essentially restoring. You'd have to read the paper. It's a whole story of how it happened. But suffice to say, the clam landings in Shinnecock Bay are up 40-fold since we began the program, right? And that's in a time when everywhere else in the South Shore, landings were flat or decreasing. So go ahead and check out that paper if you're interested. So, because it's restoring bivalves, it's restoring seagrass, and the whole ecosystem coming with it. We've been doing a lot of work using seaweeds, specifically kelp, and other seaweeds as well, that can take up carbon dioxide, take up nitrogen, produce oxygen, and maybe even fight harmful algal blooms. And we've been thinking a lot about what happens when you co-grow shellfish with seaweeds. Instead of just having bivalves, adding in seaweeds. And what are the consequences of doing that? Well, firstly, by taking up CO2, they protect the bivalves from ocean acidification. In addition, they produce oxygen and make our waters more oxygenated. In addition, they actually release compounds that can fend off harmful algal blooms and actually reduce the levels of toxins that get into bivalves. And finally, we even have evidence that the seaweeds themselves can be food for bivalves. So for all these reasons, having these two organisms together only makes sense. And again, I'm pointing out a bunch of papers here that we've published in the last few years. They're all free online. Happy to get you the references. And then the last thing I want to talk about is aquaculture itself as a clean water solution. And specifically, want to talk about a project led by Mike Dole in my lab, supported by the New York State Department of Environmental Conservation, looking at the aquaculture of oysters, concurrent with the aquaculture of kelp, which I've shown before, and another seaweed, ova. Now, kelp, for those of you who don't know, loves it cold. Right? We put it in the water in December, it grows like gangbusters. It starts dying off come May or June, so we're getting it out of the water by then. But that's the time when ova does really well. And specifically, note the word up there, bioextraction. So looking at the concept of growing the organisms, getting them out of the water, and when you've done that, you remove the nitrogen out of the ecosystem. Turns out Mike spent about a decade as an oyster farmer, so he has some experience in doing all this. So he did all sorts of calculations, looking at the rate at which, well, that wasn't just based on calculations, but we did a lot of field work too. I'll show that momentarily. But essentially seeing the rate at which the organisms grow, how much nitrogen and phosphorus and carbon they have, and then looking at what's a normal design of an aquaculture farm. And again, this was supported by the DEC. We've looked at many sites, but for this particular study, we had really good data on 3 sites in Long Island Sound, from the East River out to Mount Sinai Harbor. And I'll just put up here, the big tagline, which is that you can remove a lot of nitrogen with seaweeds and oysters, right? The key player depends on where you are, but you can see out on Long Island, oysters are doing the heavy lifting. I will say that we think we can get the seaweed numbers even higher. We're working on technologies for getting that out. But that's a lot of nitrogen coming out. You can see in some cases it's hundreds of kilograms of nitrogen per year per hectare. And so what does that number mean to anybody? Well, for perspective, one IA system gets out 7 kilograms of nitrogen per year. And we did some math. If you dedicated 1% of surface waters to aquaculture, specifically doing bivalves and seaweeds, in some systems you could get rid of 20% of the nitrogen that Suffolk County has said should be reduced. So it's one of the tools in the toolbox. And maybe this is something that should be a credit program. There's credit for septic systems. Maybe there should be credits for aquaculture. So with that, I'm done. I've told you that excessive nitrogen loading from wastewater is an ongoing threat to our coastal ecosystems and human health all across Long Island. And climate change is a compounding negative effect here. It's accelerating and making a lot of these issues including harmful algal blooms and low oxygen, even worse. Upgrading septic systems is the primary mitigation strategy for reversing poor water quality, and there's now $65,000 available for you to do that. And then finally, bivalve aquaculture combined with seaweeds can help mitigate excessive nitrogen loading while septic systems are being upgraded. So with that, I will stop, and I will thank all of you for your interest and attention in this topic.